Perfect, thank you. So it's my pleasure today to have Michael Pazzani giving our AI seminar. So Dr. Pazzani is a principal scientist at the Information Sciences Institute at USC. He was the Vice Chancellor for Research and Economic Development at the University of California, Riverside, where he was also a professor of computer science with additional appointments in statistics and psychology. From 2006 until 2012, he was the Vice President for Research and Economic Development at Rutgers, the State University of New Jersey, where he was also a distinguished professor of computer science. Prior to his appointment at Rutgers, Dr. Pazzani was the director of the Information and Intelligence System Division at NSF. In addition, he coordinated NSF Homeland Security Research. He also served as a member of the Board of Regents of the National Library of Medicine at the National Institutes of Health from 2003 until 2005. In 2019, he was appointed to the Defense Science Board. And today he's going to talk to us about expert-informed, user-centric explanations for image classification with deep learning.
Okay, thank you very much, and thanks Mabel and Elma for setting this up. This is the first talk I've given live in quite some time, and it's welcome. It's good to be back. It'd be better if it worked. Okay, so what I want to talk about today is expert-informed, user-centric explanations for image classification with deep learning. And essentially, in this area here on the, we have a explanation of why this bird is a particular bird developed by modern explainable AI methods developed in the last 10 years. But prior to that, people had other ways of explaining things. And I'm going to argue that the other ways are actually better than the new ways. And we need to find ways to get our AI systems to explain things the way experts do, instead of explaining to experts how our AI systems work. So there's really different goals for explanation in image classification. Most of it is developer-centric. You can prove to people who know about computer science why your system's working, what it's attending to. I'm going to argue instead for expert-informed, that is informed by how experts explain things, and user-centric, which meets the expectations of the users. And in some ways, over the past few centuries, experts and users have developed a way of having explanations, and this new way of explaining explanations is alien to experts and to users. I'm also going to talk a little about how explainable AI identifies important areas of images, but it turns out it needs to be more accurate at that. So even the task that it's trying to do, it's not perfect at. There's room for improvement. One way is to do that improvement is to use ensembles of learners, not just a single learner, to identify important regions, as we've used ensembles to improve the accuracy of learners over the past couple of decades. Then I'm going to talk about identifying diagnostic features for explanations using multitask learning, and then show some experiments that show that experts prefer explanations like this, and users learn faster when you give them explanations like this. So as a quick background, in the past decade or so, convolution neural networks really have revolutionized image analysis. And you essentially feed them examples, lots of examples of different birds, grebes and goldeneyes, and then it learns to distinguish them. And then you present it with a new image, and it classifies it automatically. It's found lots of applications, including in medical diagnosis. I'll go back and forth between birds and medical diagnosis. The birds are more approachable to many people, medical diagnosis being a little bit more important, perhaps. But also when we run human experiments, I can usually get 4 or 5 ophthalmologists or radiologists talk to me, but I can actually get hundreds of bird watchers to participate in experiments. And so it works out better that way as well. So then explainable AI has come up to identify the important regions of images. So for instance, if you look and see that there's a dog in the image, and then it can explain why it came to the conclusion there's a dog in the image by highlighting the dog. And similarly, if you ask, is there a cat in the image, it can highlight the cat, which is pretty cool. The first time I saw this, I was very, very impressed. However, that still isn't really doing what experts do when they tell you this is a bulldog or this is a Siamese cat. But as a way of background, in explainable AI for imaging, there's a couple different approaches. Some of them are bottom up. They manipulate the image and see how that impacts the classification. Things like obscuring image volume or image shape are examples of bottom up methods. And then there are top-down methods, and these are even divided into two parts. One type examines one particular layer of the convolution neural network, things like GradCam, for example. Others are modified backprop. They sort of do the inverse. They propagate from the output into the input, things like deconvolution or layer-wise relevance propagation are examples of that. And there's been considerable progress, lots of different algorithms. However, I'm actually going to argue that all of these algorithms really aren't solving the task that users want. And what users want is explanations like they've been receiving all along. The tools have proved useful for a couple of things. So first of all, they're useful for identifying when your decision's based on irrelevant information. So on the top, there's an example of a neural network was presented with 500 images of huskies, 500 images of wolves, and asked to distinguish between them. And what it was actually doing is distinguishing between the background. The wolves were taken on snow, the huskies taken on grass, and so it really distinguished grass from snow. And the explainable AI algorithm lets you figure out that you're focusing in on the wrong area. There have been experiments with human subjects, explaining to them we're going to highlight the important area, and human subjects can distinguish when your AI system is focusing on something that's irrelevant from focusing on something that's relevant as well. And so, that's great, but I'm going to argue that's not enough. So on the top, there's explainable AI systems that have been developed in my labs, but they're similar to ones that have been developed elsewhere for doing things like bird classification, glaucoma detection on a fundus, a photograph of the back of the eye, melanoma detection of a mole, or COVID detection from an X-ray. And then on the bottom are what you find in bird guides or medical journals. So when I look at a bird guide, it doesn't highlight areas, it points to them with arrows, but more importantly, it actually labels them, names what it is about these regions. Similarly, the ophthalmologists, if you read the journals, they'll point to a particular area of the photograph and say things like there's PPA here and rim notching over there. Or when you're doing melanoma diagnosis, it points to different parts of the mole and explains it. So it's not, and then I was given an NSF grant to deal with COVID. And again, the COVID x-rays, when radiologists look at them, they annotate them with arrows with semantic meanings. So there's, ground glass opacities here, or pleural effusions there, for example. So it really gets to the question of what's the role of an explanation. If it's developer-centric, it explains how the network works. If it's expert-informed and user-centric, it creates explanations like those of human experts, and it explains to others how to do the task. So we're fortunate to have a paper accepted in Ophthalmology Science, Ophthalmology Journal, in which we showed that one of our learning algorithms was more accurate than others. And we also showed that it concentrated on a particular area of the eye, the rim of the optic nerve, in diagnostic glaucoma. However, one astute reviewer said, you've only done this on average. You've shown it concentrates here, but on any particular image, you haven't shown that it highlights what the ophthalmologist highlights. And so we've actually tried that with limited success. So here's an example of putting these heat maps over a color fundus photograph used in glaucoma diagnosis. And actually, the database that we had is also annotated with the clock angle. So you have thin rim at 3 o'clock or 5 o'clock, etc. So we're able to get 95, 98% accuracy in diagnosing glaucoma. But it turned out that if you look at the location explainable AI was highlighting, it was slightly better than chance, but nowhere near as accurate as the ophthalmologists that didn't agree with what they were doing. Lots of reasons for that, but actually, if you run the same algorithm starting with different weights on your hidden units, which are different random weights, different orders of examples, you get very similar accuracies, but you actually get different explanations, which is sort of odd.
Yes. So you're going to explain how it's possible that you get such accuracy without concentrating on the right place?
Well, it's probably because I am, yes. But then there's a number of reasons. One is, we'll keep going. Let's see. Because you don't need to look at the entire image, actually. And by the way, it's not just my lab. So if it was just my lab that couldn't do this, that's one thing. But there's starting to be a series of articles appearing that says these explainable AI algorithms are great, but they're not really finding the locations that people think are important. So there's a very good article in Radiology Artificial Intelligence, which they did a much more careful study than I presented there. We get negative results. We don't publish them, we move on, and they actually tried to analyze why they were getting the negative results. So one reason is that deep learners just find one sufficient means of distinguishing examples, not every relevant. So as long as you can distinguish the positives from the negative, you don't have to look at all the areas. By the way, there's also other reasons. If you look at some of the math behind deconvolution in particular, it's very, very sensitive to the third or fourth significant digit. You're propagating something through 50 layers of hidden units back to the output. When you propagate it forward, it corrects for that. But when you propagate things backwards, a difference of 0.001 in one of the weights has a drastic difference in your explanation, but not a drastic difference in your in your classification. So in this case, there's two different ways, two different field marks, birders called them, of distinguishing this bird from others. It has a very odd patch on the face and an interesting stripes on the wings. And if you run the neural network two different times, one of them concentrates on one, the other concentrates on the other. One of the things we're going to talk about, I'll show some examples, is not just using a heat map, but finding the center of mass of that heat map. So it's the point on which you could balance the heat map if each of the weights were a weight, if you like. There's the nice equation from physics for center of mass. And so one of the things we're going to try to do is exploit the variability of different networks to increase the accuracy. So you can reduce the error in your heat map by averaging over multiple heat maps, which is, of course, what people did with accuracy and error 20 years ago. And in some ways, it was sort of fun doing this project, this particular one, because it was almost replicating some things that I'd done 25 years ago with a different metric. Is the explanation accurate as opposed to is the classifier accurate? So on the top, you see examples of 4 different heat maps, and then the average heat map does a better job at localizing it. In this case, we weren't training on bird species. We were training on bird wing pattern. Is it a solid wing or a wing bar or a modeled wing, for example? In the lower one, it shows the average, the center of mass of the heat maps over 11 different runs. The red one is the center of mass of the average heat map, and the black ones are individual runs. And you can sort of see that the red one does better on average than the black ones, although you can always find one particular black one that does particularly well, but that's almost by chance. So like in averaging for accuracy, you can always find one model that's a little bit more accurate, but you're reducing your risk quite a bit by averaging over multiple models. So how do we do this? Well, simply we create n different networks, And there's a couple different ways we've looked at creating N networks. One is using random weights, and that's sort of the most common. Another is using bagging or bootstrap aggregation. So you create a new training data by sampling from the old data with replacement. So some examples are there twice and some examples aren't there. It presents extra weight on certain examples and no weight on others. Or you divide your training data into N buckets and you leave out one of those buckets. So you have less data. And it's been shown that both of those methods improve the accuracy. And so we wanted to see if it would also improve the accuracy of the explanations. Bagging has turned out to be more popular these days, and we'll see. Then you can use any explainable AI algorithm to create a heat map. And then this works for all networks and all explainable AI algorithms. And you combine the heat maps. Now, right now, we're just doing a simple average, but if you look some of the more modern methods, XGBoost and others, weight certain learners differently than others, that we're reserving that for future work right now, just doing the simple average. And then we looked at two different data sets. One that we've been collecting, we call high-res birds, because it's high-resolution bird images. Right now, there's 14,000 images divided into 66 different classes. And by the way, the classes were specifically chosen so that it has contrasts of very similar birds. You distinguish them by one or two differences, a Western grebe versus a Clark's grebe. It's the pattern over the eye that's a big difference. And then we have a number of attributes. We actually have this labeled by undergraduates. Does it have a short bill or a long bill or a solid wing or a spotted wing? And then they gave us the location of some of the parts, like the bill is here, the wing is here, as polygons over the images. And then we also looked at a melanoma data set. This is an example with about 2,500 examples, two different classes. Is the mole melanoma or not? 5 binary attributes. Are there white streaks? Is the border irregular? Things along those lines. As an aside, some early examples of applying AI image processing to melanoma discovered that if you have a picture of a ruler in the image, you're more likely to have melanoma than if you don't have a ruler in the image, because they use that to measure the size of the mole, and they only do that if you have melanoma. So we've used images without rulers in them.
You have a question in the Q&A.
Oh, okay.
Do you want me to read it?
Sure.
Why don't people train classifiers to recognize component features like long bill and white wings that were used in early work on zero-shot learning, then use those features for explanation?
Well, that's the end of this talk, so that's in fact what we're doing, but we'll get to that. Okay. So indeed, that is what we're trying to do, and arguing that's a better way to do the explanations. Let's see. So now getting back to the ensembles. So what we wound up doing is comparing the ensemble average to the individual averages, and we either did the average of N heat maps, like with that red arrow, looked at the difference between the average and the ground truth. So this is a distance measure, and that's when you have a key point. And then the individual average is just when you run a single run. And then there's then we used intersection over union. It's a measure of overlap. So if you have a complete intersection, you've identified all the relevant areas. If the union is larger than the ground truth, then you've identified some irrelevant areas as well. So the intersection over union is a good measure, is one measure people use in the field to identify if you've identified regions correctly. So here's some examples of running the classifier. So we used for the high-res birds on bill size, the individual average turned out there. The ensemble has about a 10% improvement. And that's what you sort of see on ensembles for accuracy over individual ones. So we're seeing, 5 to 10% improvement. And that turns out to be somewhat important. So if you're trying to draw an arrow to the bill, being off by, you want to be as close as possible to the bill to make this work. Similarly, for wing patterns, the ensembles made a difference. And this is using VGG, one of the earlier convolution neural networks. Using ResNet, we saw about the same thing. Again, this is using center of mass distance just on the bird wings, but works on the others. And then with melanoma classification, we actually had better regions. So we used intersection over union, and here higher is better. And again, the ensemble, no matter which learning algorithm we used, improved upon that. And then we also looked at the different contribution of both the intersection and the union. So if you increase the intersection, you're finding more relevant areas, more overlap with ground truth. And what we found is the ensemble mostly increases the this intersection. In some cases, it somewhat decreases the union, but not that much. So it's better at finding relevant areas than it is at eliminating irrelevant areas. And in part, that gets back to a single model finds one sufficient cut through the data. Multiple models find multiple cuts and therefore multiple features or multiple parts of the region. Just real quick, different approaches to generating the models using the K-fold or the bagging also improved over it. So really any way of generating different models, and this has been found again when reducing for accuracy. However, people have found ways to weight certain examples, certain regions with accuracy, and so far we've not come up with ways of doing that for accuracy of explanations. And then looking at varying the size of the ensemble, you see that there's diminishing returns after a while. Averaging over 2 gets you some increase, 4 a little bit more. And somewhere between 8 and 16, most of our models sort of plateaued and there's diminishing returns. Now with random forests, people are doing thousands sometimes. So it's an interesting thought as to whether to extend this out, but you get criticized enough by reviewers when you run 8 neural networks to get a 10% improvement. So I didn't want to run 8,000, nor half the time. Now the question is, can experienced birdwatchers tell the difference between explanations produced by a single model or averaged explanations? So on the left, we have 3 different bird species marked up by Lyme. And on the right, we have them marked up by average Lyme. Now, one of the reasons we chose Lyme is it actually uses a super pixel approach. It identifies regions of the image and then tries to figure out which ones are most important. And that super pixel tends to overlap with the regions of the bird better than just the heat maps of GradCam and things like that. So with GradCam, you often get things centered on the bird, but going outside the bird, looking into the background as well. So we generated images like this, and for this case, we presented it to birders, and we asked them to, well, first of all, we asked them to identify the bird. So through bird mailing lists, we found experienced birders, offered them $25 Amazon gift certificates for participating, and then showed them highlighting and asked them 2 questions. Does it emphasize the areas of the bird that they think are important, and would they recommend using this particular highlighting? You'll also notice that we really didn't use the word explanation in there because it's just highlighting important areas. That's not real. I don't think that's really an explanation because it's missing the diagnostic features. But nonetheless, we're asking the question, are you finding the important areas of the bird? So this is a IRB approved study. There were 28 participants. Each person saw 48 images, 24 by average Lyme, 24 by single Lyme. And we asked them, we looked at the median ranking of how is it finding the important region and would you recommend it? And in each case, the average improved significantly over the single Lyme. So the birders were able to distinguish the better regions found by averaging over multiple models. Okay. Now we're going to actually get to the question that came up in the before, which is what about features? So, would you trust a robot to identify removing cancerous molds? And then if it gave you an explanation like this, just highlighted the whole thing in red, that might not be sufficient. Where if you said it's got an irregular border, it's got white streaks, variable colors.
Aren't these two completely separate questions? Would you trust it to identify? Would you trust it to remove it?
Well, we're going to automate the whole process. Actually, robotic surgery is pretty good these days.
Well, so it could be that once a doctor diagnoses it, I'll trust the system to remove it, or vice versa, right?
Yeah. Okay. No, I agree. So it's really, would you trust it to identify, and then to remove? But you're all right. That's interesting. So, I think it's equally accurate at both, but nonetheless, not there yet. So let me give you some more comments on explainable AI, and this is just using heat maps to highlight images. So one reviewer of a paper that we submitted to a radiology journal said it's not the method that gives you the interpretation, it's the expert. It's the one who looks at the image and attributes that feature to one particular meaning. So it's not that it's this region, it's that there's ground glass in this region, it's a radiology term. And then one of my grad students, one who ran the experiments, gave this quote: I was humbled to witness the contrast between what many researchers in the field of explainable AI makes think is an adequate explanation compared to what the end users actually desire. And what people desire is identifying not just regions, but diagnostic features. So in melanoma, you can find charts in your doctor's office or on the web. And there's a number of things such as asymmetry, or look at the border, look at the colors, and there are more than one color, look at the diameter. And so can you use these terms in your explanation? And actually, here's an example. My wife gave me permission to show part of her electronic health record. And after an eye exam using the same sort of fundus photography and also OCT, the ophthalmologist creates an image that shows where there's some irregularities in the eye. It doesn't even superimpose them over the photo of the inside of the eye. It just says, over here, you got a little problem, and over here, there's a little problem. So that's our goal. Our goal is to do things along these lines, but before we get there, let me actually ask if birders would prefer if we do this. So in another experiment, we showed experienced birders 5 different ways of doing explanations. One is with the heat maps that come out of explainable AI. Another is with bounding boxes. So some of the systems, instead of a heat map, will use a bounding box. A third is just arrows that point at things. A fourth is our preferred method, which is arrows with semantic labels. And the fifth is pure text. So there's actually birding applications that identify birds for you. And then they'll show you a picture of the bird and give you a pure text explanation. And often it says, I'm not sure it's either this one or this one, but then you have to read through the text and figure it out. And it's not that helpful, in my opinion, but we'll see. And then we asked them the same questions that we asked earlier. Would you recommend using this way of highlighting to identify the bird? Would you recommend using this to others? And the quick result was that on average, expert birders preferred labeled arrows with semantic labels to other techniques. Verbal descriptions were a close second, but the heat maps used by explainable AI were a distant fifth compared to the other methods. So there's more to explanations than what people have been looking at. Then we asked the next question. Did I skip over one? No. Do novices learn faster when given diagnostic features? So in this case, we had novice birders, actually UCSD undergrads, and we eliminated ones who had experience with birding. And then we asked them questions like, is this a Clark's grebe or a Western grebe? And then we would show them yes or no, and then we would give them an explanation, either a heat map or labeled arrows like before. So we would say things like, this bird's got white spots on the back, or this bird has a solid wing. And not surprisingly, they learned faster when you had the semantic label and when you pointed at the area. So in the 3 different bird species, that held true. And again, the heat maps, present some useful information on the area, but it left it up to the person to figure that out. So then how do you learn to label with diagnostic features? One of the people who asked a question who could spell features better than me wound up coming up with the solution we've been doing. So we're training, all of our training data we associate with a class. Optional, we actually have a super class. We've also been experimenting with including things like what its diet is. Does it eat seeds or does it eat insects? Because that gives you some information about the bill shape, for instance. But then we also annotated with these diagnostic features. Is there a red eye or a yellow eye? Is there a stripe on the wing or a solid wing? And we used multitask learning to simultaneously learn to classify and to detect the features. Then you can compute the heat map for the class, optionally the superclass, and a heat map individually for each of the diagnostic features. And you compute the center of the mass for the diagnostic features, and you use labeled arrows to point to all that. So this is what it looks like in a neural net using multitask learning. So in this case, there's 4 different tasks. You give it an image, you ask which family it belongs to, which species, which bill length, whether it has a ring around the eye, but you can keep going on and imagine 20 diagnostic features here. And if you put it all together, this is what we some of the results are. So we're able to identify some of the diagnostic features and come up with the class, superclass, and getting closer to being able to produce what is in the bird guides that you see. Now, it's not perfect. If you look, we're off a little bit by the medium bill is pointing to the chin, not quite the bill. For some reason, it thinks that greater scop belongs to the superclass owl instead of duck. But that's what you get when you have 95% accuracy. But I think we're getting closer to producing explanations like experts produce, and not surprisingly, we're now applying for grants to apply this to medical domains. So let me tell you a little bit about our current and future work. Some of our future work involves few-shot learning. Yes.
So I'm sort of 95%, accuracy without asking, right? But that meant, birds may not have been classified correctly, but you have like a photo that is not of a bird at all, or is it?
All those are birds. Which one?
The one on the top left, top right.
Yeah, maybe that's a little gray. It doesn't show up that well, but yeah, that
So
was,
it is a bird.
yes.
Okay. Have you tried applying this to other photos entirely to see what happens with them? Because that can happen sometimes. There's all kinds of features that.
Oh, I mean, you train it on birds and then you show it dogs?
Yeah.
Without ever any training on dogs?
Yeah.
Ooh, well, how about this? So getting back to the future work.
Just thinking about.
We've shown this picture, which is not of any of the species in the data set. And it has a rather distinctive feature, an extremely long bill. So this is called a sword-billed hummingbird. So it actually identifies this, it gets it as a hummingbird, but it does, we'd like to create another dimension on the bill length of very long. I mean, that's not just, or extremely long. That's not just very long. I think it's the only bird whose bill is larger than its body, but you can learn this in a single shot, can't you? I mean, if you see another one of these, you're going to say it's a sword-billed hummingbird.
One species of bird that has that.
Well, that's actually the interesting part, which is the most diagnostic features are the most rare features. So a red-footed booby has red feet. There's not that many birds with red feet. You see that, you come up with that. So, but for deep learning, rare features are the hardest things to learn, but for people, they're the easiest. So we would like to be able to replicate that. And some of the things that came up with the question of one-shot or few-shot learning are there. Now, it turns out I've been talking about diagnostic features and descriptive features. Not all descriptive features have high diagnostic values. So if you're creating an explanation, you might be able to identify that this bird has black legs. Well, nearly all birds have black legs, so it's not that important. So how can you tell them, how can you decide which of the features that you can identify to put up there? And well, there's been, a number of approaches. One is using Q validity. The probability of the feature given the class is high. Oh, did I get that backwards? Class given feature. I think I did. I'll have to think about this when I'm not standing up. There are explainable AI methods such as SHAP that you can use. Also, people look at contrasting features, not what is the difference between a spotted towhee and an eastern towhee, and the big difference is the spots on the wings. So if you're trying to ask the question, why is it X and not Y, a contrasting method. We've also been looking at just the overlap of the explainable AI region. So this is why it's a spotted towhee. And this is why it has spots on the wings. This is why it's got a black foot. Well, the black foot doesn't show in the explanation as why it's a towhee. So then you might not need to include that in your explanation. But we're playing with a number of things. If our grant is funded, we'll actually do it for real instead of think about them. Another thing we've been doing is I've been fortunate to have some colleagues who I've been able to convince to put some effort into this in glaucoma. So they're actually annotating the glaucoma images with this region has this particular defect. So the rim is then there, and there's an RNFL defect over there. And then one of the things I'd really like to be able to do is discover new diagnostic features. So here's an example of 6 different patterns of a bird wing. We don't actually have good labels for the difference in English for these. I would call them all modeled, but I actually showed these to the best bird watcher I know, and he was able to identify each of the 6 birds from just that wing, which is pretty cool. But he watches birds for a living. That is, he counts birds for the National Wildlife Society and things like that. So, all right. Well, let me start to wrap up. Take questions. I realize this went a little bit faster than I thought. I could have thrown more in. If you're interested in this, here's some recent papers in cognitive science on the psychology, a AAAI paper more on the philosophy, and then the ensembles paper just came out last week in this conference. So the quick summary, explainable AI should be informed by explanations. The regions of interest identified by explainable AI algorithms should correspond to the regions that experts think are important. And averaging over multiple models improves this. And then we were able to show that experts preferred that. But experts also prefer explanations that include diagnostic features and their locations. Users learn faster when you have this. And then we've done multitask learning for classification and diagnostic features. And then we adapt the existing explainable AI algorithms using center of mass of regions of diagnostic features. And let me stop, take questions, thank DARPA's Explainable AI program and NSF's program for funding the earlier research, and a bunch of people to thank, including Dave Gunning for really for pointing out that this is an important problem and convincing the U.S. government to put some money behind it. David Aha, some grad students at UC Riverside, collaborators in radiology, and on the bottom are the 4 graduate students at UCSD I worked with on some of this. So happy to take questions and have a discussion.
Thank you. There is one question in the Q&A, so I'll read it to you. How much of your analysis is specific to deep neural networks and how much generalizes to other approaches to visual recognition?
Good question. So I think it certainly generalizes to transformers and other, so convolution neural networks, transformers, I think it applies there. Earlier approaches to computer vision actually tried to develop recognizers for each of the little features. And some approaches have developed recognizers for each of the features, sort of by hand, and then applied a machine learning, like even decision trees or other things, to take those diagnostic features and map them to classes. So I think other approaches to computer vision are applicable. And in some cases, I'd like to use some of those. I mean, there's no particular reason that we have to have undergraduates identify the eye color of 14,000 birds when you can write a computer algorithm to find an eye pretty easily and look at the iris color. As an aside, we had 7 undergraduates mark up the data, and we discovered one of them had red-green color blindness in the process and had to discard his data as well. So,
I guess a bit of an elaboration on the question I had before. So there is a prior process that goes on here that is already done by people with some expertise or not, like saying, these are pictures of birds, okay, as opposed to other things. Or this is a picture of a mole, and now we can have the system try and figure out if it's a cancerous mole or not, right? And as I think you pointed out earlier too, right? If that initial selection isn't done correctly, you can get artifacts like figure out that the cancerous moles all have a ruler, right?
Mhm.
So how well do you know that that didn't happen even with these other with the selection process that you did settle on in the end? And that's I brought to the question from my earlier one about, if you have other animals in there, will it still be able to detect even the fact that it's a bird, forget the species, right?
Yeah. So in general, as you know, machine learning almost has the assumption that the distribution of the test set is the same as the distribution of the training set, and that's not always true. So, for instance, in melanoma diagnosis, we've been able to find very few examples of dark-skinned people with melanoma. Now, it turns out fair-skinned people get melanoma more often than dark-skinned people, but it looks differently on people with dark skin. So I don't know if you know, Bob Marley died of melanoma, and he thought it was a bruise. And we'd like to be able to, first of all, identify that you're biased in some way. Sometimes you can do that with the husky example, the background difference. But you're right. If you have something totally alien, you can probably identify if you do things well, it doesn't fit within any of your existing classes. So I've got to choose the most likely out of 66 classes, and one of them, it's often the case, one of them is 0.9, and then all the others are lower. If you have 0.6, that's probably a good sign that something that you don't quite identify it. But even with the glaucoma work that we're doing, so I have a collaborator now who's looking at this and collecting data from different distributions in Los Angeles than you normally see in the public data sets. So I think it's real important to have this representative data. I'd love to work with others on how to identify that your data is not representative. But
the reason I'm asking is it's perfectly reasonable to expect that if you want to automatically identify the type of, potentially cancerous growth someone has, someone will select the right things before. But if you want to use something like this to, I don't know, for automated driving, right, where the camera's just looking out and trying to figure out if you're going to hit a person or something else, then you can't control ahead of time what kind of scene you're going to be looking at.
So I do agree with you. So, for instance, I have had the experience of driving in Australia on a dirt road and having kangaroos jump in front of my car. Okay, now this is something probably Teslas aren't trained on as well. And in fact, I did read that predicting the trajectory of hopping things like kangaroos, it just wasn't considered that well. that's a problem for someone else. But yeah. I mean, but it's a good question. But unfortunately, what happens? You get funded by the National Eye Institute to look at this narrow problem, and sometimes you don't look at the big picture. However, with myself and my grad students, I think we've taken a step back, and we've actually done things like recorded radiologists as they're analyzing images. So when I call this expert informed, it's informed because we have interviews with radiologists watching them. And also we just look at the artifacts they produce, the journals and things of that, and we want to produce what they produce. But yeah, there are radiologists who are birdwatchers or radiologists, or other things, and they can do both of those tasks. And so, mostly we develop fairly narrow systems. Far too often, we actually also develop narrow systems because they don't identify every eye disease. You have a glaucoma specialist, and then you've got, a diabetic retinopathy specialist, and you have lots of these data sets, healthy one disease. You don't really have a lot of data sets healthy in 14 different diseases.
Your question makes me wonder. I mean, a lot of this presumably comes up in autonomous vehicle control questions. The idea of distinguishing between the accuracy of the prediction and the accuracy of the explanation. I mean, the example you were giving about identifying and removing a cancerous mole, I mean, imagine identifying a red light and stopping at the red light.
Mm-hmm.
It's a very, I assume that these methods, for example, of using ensemble learning have probably, I don't know, maybe this has been considered was probably a pretty large literature for autonomous vehicles. Is there anything that kind of can be extracted from that that's relevant here?
Well, I mean, I've certainly seen lots of ensembles for accuracy. To my knowledge, this is the first doing ensembles for explanation.
But
to be
for self,
yeah. Well,
explanations, I kind of your answer also.
Well, let me give an example of those. So here's something that Tesla did pretty well. So there's the should I change lanes and my car beeps. A Tesla shows you the cars next to you. Now, it's sufficient not to change lanes to say there's one car next to you, but it actually shows all the cars next to you. And I think this is a good thing, because if it showed one car next to you and that moved, you might think it's safe to move over, where it's really not. So, but on the other hand, that's not using explainable AI to do that. That's using, a well-designed car detector. I have chatted with people. It's sort of interesting. They come up with their own explanations. So my lane changer doesn't work perfectly. And it doesn't work as well for motorcycles. Well, I can believe that. They're smaller. And I know how it's working. But, I was chatting with one person who thought it didn't work well for white cars. Now, that might be the case. But if it's using LiDAR instead of vision, that's probably not the case. So.
BMW does fine on motorcycles.
What's that?
BMW does fine.
Really? There's been a test of
I was surprised.
Yes.
Bicycles.
The bicycles is tough. Self-parking cars, it's not fully automated. Hit 30% of the bicycles. So
That to me is a question of accuracy of explanation. Yes. I mean, you're identifying kinds of objects, and you're failing to see what's important in this set of segmented objects. So I think it's I mean it may not be viewed as a question of explainable AI in the autonomous vehicle literature. I don't know.
I don't think that comes up as much, and it's actually also an interesting question of how important is an explanation.
Right.
Okay, so I mean, there are certain things. So we trust bomb sniffing dogs. It's a neural network and olfactory sensor, and it produces a certain output. Interestingly, drug sniffing dogs, they have to retire a number because marijuana is more legal, and there's no way to tell the dog, tell me about cocaine and heroin, but not marijuana, after you've trained it in all three of them. So there may have been an advantage to having an explainable AI system that you can provide that sort of feedback. I should say there's a whole area that people talk about, and I don't think it's been done perfectly yet on advisable systems. So you should be able to turn your explanation around, right? Now I explain to you why it's this bird. You tell me a new bird and it's got purple feet. And now can you incorporate that into the neural network? Some of the few shot learning can. It's just never been coupled, to my knowledge, with explainable AI, correcting explainable AI. There's been a little work on Lyme, a system actually called Lyme Aid, but it's not perfect yet.
Any more questions?
Thank you very much.
Thank you.